This is the second video of Unit 2 on the different methods of formation of metal carbon bonds of the main group elements. Another interchange reaction is metathesis, which consists in the reaction of organometallic compounds with metal halides. This is probably the most widely used and versatile method in the laboratory for the preparation of organometallic compounds. In these exchange reactions, the direction is such that the halogen will combine with the most electropositive element and the organic radical with the most electronegative one. By far, the most widely used reagents in such synthesis are the organic derivatives of lithium and magnesium, which react rapidly and exothermically with halides of the more electronegative elements. Organolithium compounds are more reactive than Grignard reagents and, in certain cases, allow more complete substitution. For example, Grignard reagents substitute only 2 of the chlorine atoms in thallium-3 chloride when the ethyl ether is the solvent, whereas alkyl lithium replaces all 3. Similarly, platinum-2 dibromido bis triethylphosphane yields the dimethyl derivative with methyl lithium, whereas the Grignard reagent gives only the monomethyl complex. Another factor which influences the choice between organolithium and Grignard reagents is stability against hydrolysis of the desired product. Grignard reaction products are conveniently isolated by hydrolysis of the reaction mixture with diluted hydrochloric acid, a saturated solution of ammonium chloride or water to destroy any excess Grignard reagent and to dissolve the magnesium salts, followed by separation of the organic layer, drying of the organic phase, and finally removal of the solvent. If this is not done, an intractable mixture is obtained. On the other hand, lithium alkyls can be obtained in petroleum ether, hexane, pentane, heptane, etc., in which lithium halides are quite insoluble. Water-sensitive reaction products can be separated by filtration of the lithium halide and evaporation of the filtrate in a dry atmosphere. The addition of metal hydrides to alkenes and alkynes is known as hydrometallation reactions, which can be considered as the insertion reaction of the alkene or alkyne into the metal hydrogen bond. The most important examples concern boron, aluminium, and silicon. That is, hydroboration, hydroalumination, and hydrosilylation reactions. We'll talk about hydroboration and hydroalumination in Unit 3. Addition of silicon-hydrogen bonds to alkenes and alkynes, hydrosilylation, is used in industry in the production of silicon derivatives. Addition may occur by thermal reaction, under UV irradiation, or using a catalyst. Several transition metal catalysts, such as those in this figure, have shown to be useful under different conditions. The silicon-hydrogen addition can be of two types: beta addition or anti-Markovnikov, which is the most frequent, or alpha addition or Markovnikov. Markovnikov's rule says that hydrogen from the added molecule will bind to the carbon atom with the highest number of hydrogens. Carbene insertion is another method to form metal-carbon bonds with main group metals. Diazomethane is a poisonous yellow gas. In liquid state, it is explosive, behaves like a nucleophile, an electrophile, and is also a source of carbenes. Diazomethane reacts easily with metal halides or metal hydrides, giving insertion of the methylene group. Replacement of all the metal halide groups is often difficult or impossible. Finally, we are going to talk about the metallation reaction. Metallation reactions, which consist in the substitution or interchange of an acidic hydrogen by a metal, are acid-base equilibria which are shifted to the right side with increasing acidity of the hydrogen bonded to the carbon atom. That is, the starting reactive carbon-hydrogen has to be more acidic than the corresponding product. Substrates with a very high carbon-hydrogen acidity, such as acetylenes and cyclopentadienes, can also be metallated by alkali metals in a redox reaction.